In this segment, we look at Newton's second and third laws of motion. In our laws of motion train, the second law in the second car shows the formula F equals ma, force equals mass times acceleration, and it's illustrated by two massive knights forcefully accelerating toward one another. The third car shows our skateboarding young man slipping off his skateboard, illustrating Newton's idea that every action has an opposite and equal reaction. Newton's second law of motion introduces an idea called acceleration. Now, we previously looked at velocity. Velocity is a vector, speed plus direction. And when your velocity changes, that's called acceleration. Now, this is going to take a little bit of work to understand this because you and I think we understand what acceleration is, but naturally, physics has a slightly fuller definition of this word, acceleration. To you and me, that pedal is acceleration. We even call it the accelerator pedal. When you press on it, you accelerate. You go faster and you pick up speed. And next to it is the brake. When you step on it, force due to friction slows the wheels down and you come to a stop. In physics, acceleration is any change in velocity. Remember, velocity is a vector, speed with direction. So anytime you change one of those, speed or direction, you change your velocity. And instead of always saying change in velocity, we use a new word, acceleration. Acceleration is the word that we use anytime you change your speed or your direction. So when you go forward, that's a type of acceleration because you're changing velocity. And when I say going forward, I mean accelerating forward, changing your forward speed. Accelerating forward is, of course, a type of acceleration. But also when you slow down, that's a change in your speed, a change in your velocity, so that also is acceleration. Talk about counterintuitive. And if you change direction in your car, a change in velocity, that's a change in acceleration. Try to get a feel for this when you are driving or riding in your car. When you're in your car and you're going the same speed and the same direction, think to yourself, our velocity isn't changing, so we are not accelerating. Then, if you turn one way or the other, that changes your direction. Think to yourself, our velocity is changing because we've changed direction, and that means we are accelerating. Or if you speed up, that changes the speed part of your velocity, and think to yourself, we are speeding up. That changes our velocity, and that means we are accelerating. And when you come to a stop, think to yourself, we are changing the speed part of our velocity. Our velocity is changing, and that means we are accelerating. Newton's second law of motion is F equals ma, force equals mass times acceleration. Now, if your mass changes, like the mass is changing for this truck as the beans are being loaded inside, well, then Newton's formula becomes more complex. But if you aren't gaining or losing mass significantly, like when you are driving in your car, then this simple formula has proved very useful to physicists for centuries. This is Newton's famous second law of motion. Force equals mass times acceleration. It's often turned around so it reads acceleration equals force divided by mass. As you can see in the formula, A equals F divided by m, that the mass gets divided into the force, that the mass is the thing that really limits the force, which in turn limits your acceleration. So if you add weight or mass to an airplane, it takes way more force to get it to accelerate any faster. This is exactly why airlines are now so picky about how much luggage you haul on their airplane. The second law of motion tells them the greater the mass, the more force is needed to accelerate, and they produce force by burning expensive jet fuel. The more fuel they have to burn, the less money they earn. So they charge you extra cash to pay for accelerating your massive luggage through the air. This is also why they strive to make airplanes out of lightweight aluminum and carbon composites. Newton's second law says they will save money if they do. On the surface, the second law seems like common sense. The more something weighs, the greater its mass, the more force you need to get it to move or to accelerate. Yeah, but the genius was in coming up with the formula that said it. F equals ma. Newton's third law of motion introduces the idea of twin forces acting in equal and opposite ways. The third car shows a skateboard slipping off in one action, while our young man slips off in an opposite reaction. And this is the most common way you will hear this law stated, that for every action there is an equal and opposite reaction. And that's why we illustrated the third law with our action-reaction skateboarder, because you'll hear it stated this way all the time. More accurately, the law should read, for every action from one object, there is an equal and opposite reaction from a different object. But we think one of the more memorable ways to state the third law is to say that forces always come in pairs, like these twins. Newton's twin forces. And like these twins, they are equal but opposite. Every force always comes with an equal but opposite twin force. That's what Newton's third law means. Now, why would Newton come up with this law? It's because if his first law of inertia was right, then this third law had to exist also. If objects in motion only stop because forces stop them, then every force must be met with an equal and opposite force if it's going to stop. Take the example of a hammer and a nail. When a hammer strikes a nail, we can see that the hammer has force applied to the nail. That's obvious, that's intuitive. And then the hammer stops. But Newton's first law says the hammer's lazy inertia will keep the hammer moving unless another force acts on it. But where is the force acting back on the hammer? It took Sir Isaac Newton to realize that forces are not so one-sided. Even though the nail and the wood look immovable and solid, all matter actually has a lot of elastic and flexible and compressible qualities to it, even if it's a nail. The nail actually bends like a spring. The wood flexes and compresses like a spring, and then they spring back against the hammer with an equal and opposite twin force. And that's why the hammer stops. This is the essence of Newton's third law of motion. Whenever one object exerts a force on a second object, the second object reacts back with an equal and opposite force. Because forces always come in pairs, as twins. Here are a few examples of the third law, and we will divide them into intuitive examples, that is, ones that you hear about all the time and that make sense, and the counterintuitive examples, ones that aren't so easy and not so obvious. Children often learn the third law with their first red wagon. At some point in time, they try to jump off the back. The wagon suddenly flies forward, and they get a real feel for how the third law works. This is an easy example because the wagon moves easily in the opposite direction and has a similar mass as the child. You can see the two forces. The child pushes on the wagon, and the wagon pushes on the child. It's similar when you are rowing around on a raft or in a boat. The twin forces here are the oar pushing the water and the water pushing back on the oar blade, equally and opposite. And since you have very little friction in the water, the boat moves easily, just like the wagon with the wheels did on the land. A water rocket is a type of model rocket using water as its reaction mass, the fuel. The pressure vessel, the engine of the rocket, is usually a used plastic soft drink bottle or a rigid plastic one, like this toy. The water is forced out by compressed air. The water shoots out this way, the rocket goes this way in an opposite and equal reaction. Two ice skaters of the same size face each other. One pushes the hands of the other, but they both move. Newton's twin forces. You can't push the one without getting pushed back. Now this is easy to see because they are on ice, where there is very little friction to stop them. This idea that forces always come in pairs can be pretty non-intuitive. But one of my favorite analogies of Newton's third law, his twin forces, is distance. The distance from A to B is equal to the distance from B to A, except that it's opposite. An idea very similar to force. The force from A to B is equal to the force from B to A, except it's in the opposite direction. Thus, the skaters move apart in the opposite direction with equal force. Of course, if skater A had much more mass, her acceleration is less than B, since there is much more mass, and according to Newton's second law, force equals mass times acceleration, it means that the mass is the deciding issue in how much you accelerate. In this way, you begin to see how the first law of lazy inertia and the second law of mass and acceleration and the third law of twin forces actually work closely together in all forces. These examples are probably the easiest to grasp because the reaction is so obvious. And what makes the reaction so obvious is the reduction of friction, like in space, or on the ice, or in water, or in the air. But what about everyday life, like walking around or driving the car? When I walk down the sidewalk, I am definitely moving forward, but where is the opposite and equal reaction? When you walk, your foot presses against the earth, and according to Newton, the earth presses against your foot, equally and opposite. The twin forces. That's why you move forward. When you lean against a wall, Newton's twin forces say you press against the wall, and the wall likewise presses against your hand. When your hands press or rest against a stone, the stone presses back on your hands. And how do these inanimate objects press against you? At the atom level, the electromagnetic fields meet, your foot and the earth. And the earth and the foot give, then stop, as the fields will not give anymore. Like all similar electric charges, they press back against your force equally and in the opposite direction. Your finger presses a rock which feels very solid. What you are feeling is the strong atomic structure of granite, but it only gives in a tiny bit, like an elastic rubber band, and then you begin to feel the rock refuse to give, and you start feeling the rock as its electromagnetic structure pushes back. Newton's twin forces. The finger pushes on the rock, and naturally, the rock pushes back on the finger. The twin forces are often called force pairs. Newton's third law of motion is one of the most difficult of all physics laws to really understand. So here are a few common misunderstandings that we will try to clear up in order to help you better understand Newton's third law of motion. If a truck and a car get in an accident, will the truck exert a greater force on the smaller car? Well, that's what we naturally think, but our normal physics thinking tends to be a little upside down. We believe that large objects apply a larger force on smaller objects. That is our personal incorrect law of motion. But that's not how the world is actually designed, and it took Newton to discover this. When two objects meet, together they make a force by exerting an equal and opposite force on the other. The truck and the car impart equal and opposite forces on each other. The forces are the same since they are now one force pair. But the truck is more massive, it has way more lazy inertia, and so it accelerates less with a given force. In the accident, we say, the car took the hit, meaning it accelerated much more, causing more damage. Remember, in physics, any change in velocity, speed, or direction is a form of acceleration even when you are slowing down. When a bug hits your car windshield, which one exerts the greater force, the car or the bug? The force pair on any two objects is equal regardless of their individual masses. The actual force placed on the bug from the car is identical to the force placed by the car on the bug. It is one simultaneous force. But who had the greater mass and thus resisted acceleration most? That was the car. The bug was unable to withstand the great acceleration placed on it from the twin forces due to its small mass. If the twin forces are equal and opposite, why does anything move? Don't the forces cancel each other out? If the twin forces happened to the same object, then they would cancel each other out and nothing would move. It would be like you walking 3 or 4 steps forward, then 3 or 4 steps backward. But Newton has his twin forces acting on completely different objects, almost as if they were completely unrelated. The reaction pair happen at exactly the same instant, and they happen on 2 different objects. The hammer exerts a force on the nail, and simultaneously the nail exerts an equal force on the hammer. The twin forces act on separate objects, so there is nothing to cancel. Both objects are being acted on, forced, by separate objects. The force on each one is equally powerful, and it occurs in opposite directions. There are three rules for Newton's third law to be valid. First, as we just saw, the twin forces must act on two different objects, like the hammer and nail. Second, the twin forces must always be of the same type, like two gravity forces or two friction forces. You don't mix and match forces. And third, they must be, and always will be, equally powerful and in the opposite direction. Sir Isaac Newton is considered by nearly everybody to be the greatest scientific genius ever. In reality, physics owes everything to Newton. He was really the first to use mathematics to develop his theories, and when the math was found to be inadequate, he invented his own. His 3-volume Principia Mathematica fell like a bombshell on the intellectuals of the day, for it was a work of such staggering insight and innovative execution, it is still difficult to believe that one man did it and that he did it all in 18 months. And Newton clearly saw his scientific work as a revealing of the greatness, the complexity, and the underlying order of nature and of nature's God. It is critical to grasp the importance of God to Newton, because Enlightenment philosophers have tried very hard to remove God from Newton's personal world. They said the universe was without a soul and purposeless. It is an irony that this kind of thinking is very anti-Newtonian. Newton was adamant that you could not read God out of the equation that in the universe, God was essential and absolutely present and absolutely powerful. Newton's mind always in high gear, he sought to decode the secrets of the scientific universe and to decode the hidden secrets of the spiritual universe as well. He personally owned over 30 Bibles. Many of the laws that we've just looked at seem to run counter to how we normally think. It doesn't seem that there is always a force acting on things to slow them down and to stop them. It doesn't seem normal that light and heavy objects should fall at the same rate. It doesn't seem that there is an opposite force acting on me as I walk on the earth. But as you think about these ideas in your everyday life, driving, observing, thinking, and doing a little research, they will begin to make more sense. And at least you can begin to grasp the way Newton understood the mechanical principles built into the universe. A universe intentionally filled with motion and force.